Now we're going to talk about offline reinforcement learning. So now that we've covered like DQN, we were also able to cover like continuous versions of being able to do policy gradients. Now there's basically this concept of offline RL, because there are these days data sets, many of them are labeled with rewards. Why is it so hard to be able to train a policy that'll just learn from all this offline data and not diverge? Because everything we saw on Wednesday was sort of like if the replay ratio goes too high, your entire model just basically goes off into space. Basically, it starts predicting huge values and or crashes. So we'll discuss some of the motivations why at least where deep reinforcement learning is a really good paradigm to get into, but also with anything new and anything deep RL, still the details really matter in terms of getting this to work well. So let's start with a little bit of the concepts in the beginning, and we'll revisit some of the challenges with being able to learn online, and then some more on offline RL. Okay. So like sometimes in the community, reinforcement learning gets a bad rap because it's fairly data inefficient. At least it's mostly the way people think about it. So even though we've got this loop, it might require, thousands of episodes of seeing a single state to learn, could require millions to billions of samples. If we go back to talking about the, was it Alpha Star paper? I believe that paper and the OpenAI 5 paper needed like hundreds of human lifetimes worth of data in order to be able to do well in those tasks. Don't know about the rest of you. I'm not nearly willing to wait that long in order to be able to train a good policy. So this kind of begs the question, like, all right, we must be able to address this in some ways. And this is going to get part of this lecture is a bit about offline RL. It's also a bit about different ways to think about the sample efficiency problem that we haven't quite got to yet. But one of the first components for this is kind of being basically jealous of supervised learning. Like for any supervised learning problem, you can train your model over a big pile of data repeatedly. It can overfit this, no problems with divergence. So we're not really that lucky in reinforcement learning. So it not only requires a huge amount of data to revisit thousands, many thousands of times, potentially the same state. Really, the concept here is like, is there some way to make like reinforcement learning have the same properties in terms of training when it comes to supervised learning? So could we just take a big pile of data, train it a whole bunch, nothing destabilizes, everything converges? And then we'll get more and more into like, in this process, can we also get better and better policies from that data? Okay. And then as much as this is about RL, basically nothing about this lecture is about exploration. So it's not about where to get this data. It's not about how to find it. It's just if a policy is given some data, could it just train on this and not diverge? So that at least it can like extract all the relevant information from that data. We'll have a later lecture on exploration, which is how to find good data. But this is just if you found it, can you learn from it? Okay. Does that make sense so far? Okay, great. Yeah, and this is sort of one of the common, at least images, sometimes overused in the community, because part of this criticism comes from this. Maybe because some people that are apparently very good at machine learning, but don't do reinforcement learning very often, kind of come up with this image of how, like, where to learn information from in terms of the data sources that are available. So there's this example of this cake, anyway, where unsupervised learning, like supervised learning can work well. And you basically for every data point in the data set, there's maybe a bunch of different classes. So the model kind of gains information about 1,000 different things potentially after every update. Unsupervised learning is sometimes like even better than that because it's learning to predict on top of stuff, potentially many possible outcomes, kind of like how we've thought about doing like video prediction models. So if you learn a model that'll predict the next image, it's a lot of information in every pixel that helps propagate gradients into training the model. But then kind of RL comes along and you only get very little bits of information. Here's one single reward at this state. And you have a giant model you need to be able to train from this very weak signal, is this concept. And here we're really trying to figure out Basically, can we change this cake? Is there some way that RL can absorb much more data, a lot more signal in a nice way to at least be more competitive amongst this group for being able to learn a good model? Uh, mhm. Okay. So basically, one way to think about this is supervised learning, it can overfit, which is actually a good thing, at least in this discussion. It can train over a bunch of data repeatedly. It allows it to maximize the model and reuse and extract information. We hold out some bit of data so that we like the algorithm and we can understand if it's starting to overfit. We've got a good paradigm there for training models. On policy learning, at best can reuse data 10 times before it starts to, the important sampling ratio is basically too weak and any information it gains from that data is pretty much zero. Off policy methods. So here the data reuse is a bit more fuzzy, but these can at least learn from other policies. And, the challenge is still though, okay, the more off policy that data becomes, basically increases the likelihood of this type of divergence, where the basically offline RL can't do this process. Even if offline RL, or sorry, like off policy RL wanted to, it can't overfit data. If it tried, it would diverge, pretty much all cases. But then basically, how do we overcome these two lines here? So at least we could train over some data. So the one way to think about this, at least when we get back to RL, is experience memory replay. So in this case, basically there's always that data set that the agent has been collecting so far, and then being able to train over this replay memory, which is something we've talked about a few times before. But now the new idea, or maybe one conceptual way to think about this, is how can the replay memory, basically the number of steps here for K, be increased to infinity? And that's where last time we talked about replay ratios. So basically K is a replay ratio. There was a lot of algorithms for having better sample efficiency, where this replay ratio would go. And now this replay ratios, let's just set it on infinity. Although a lot of those prior papers from Wednesday would say, okay, now this is divergence, but this is now our goal. Okay, still good? Makes sense so far? All right, so now we get into the weirder stuff. So how can we be able to increase this reuse? So if on policy can basically only learn from the current policy, one first thought would be, okay, what about model-based RL? In here, that is just supervised learning. The agent would train some sort of forward prediction model using that, and then basically just use that for some amount of planning, or use that maybe in some way to like back up information into a queue function, but we won't get to that till the end of the lecture. So this is good, and this is also data efficient. It's more like that kind of like unsupervised learning methods, where now it gets to predict lots of stuff, like many features into the future, and then propagate gradients back from all that feature information. So it gives it a lot of signal. Okay, but then what about types of off-policy RL? Are those options here? We've already covered many algorithms. The off policy technically trains from a type of supervised learning objective. At least it looks like a supervised learning objective if you just ignore that the distribution is changing all the time and that there's potentially some bootstrapping. And it learns basically on this function. Okay, this is maybe another option, and I'll return to this in a bit after we get through a few other details. Okay. So I want to talk about one of the other benefits. It's really more, let's conceptualize what is meant by extracting all the goodness from the data. It's not maybe, in types of supervised learning, it's being able to extract a good representation, something that we like hope generalizes really well to new data. But what does this process mean for RL? It's not always just trying to be able to pick, okay, where in this data set is the best trajectory? Partly because, there might not actually be a best trajectory in that data or a best trajectory in every case. So this actually introduces this, honestly, like really great concept that comes from RL that doesn't exist really in supervised learning at all. but it's a really good benefit here. And it's this idea of being able to stitch things together. So what this really means is, okay, if there was a task, and it's like a conceptual example right now, and there's some data set. So there's these three trajectories. This one obviously is not good. It never reaches the goal. But the idea is to figure out, like, because of the way RL algorithms work, and essentially when they're doing this planning process, they can figure out how to stitch this data together. So here, even if there's an example of this trajectory here that goes to the goal and this trajectory, but if the start is this location, then the shortest path actually goes here. At least it's in the data set, and then it borrows this trajectory from over there. But that didn't actually exist in the data, like not as one continuous sequence. And normally, like supervised learning can't take advantage of this. It doesn't know how to figure out how to stitch together components of the data properly. But in RL, it's theoretically possible to do this because of the Markov property. So like everything I'm talking about here depends on that, because at any location, like any state and any trajectory, that should be all the information that is needed to make a decision. That means once it gets to that state, it doesn't care about the past. It's effectively like useless to it at that point. From that point, it's just figuring out what is the optimal plan. So here with that concept, then it's possible, even if there's a big pile of data with a bunch of different trajectories together, if we can do offline RL really well, it should be able to actually piece together trajectories from different chunks of data. So like theoretically and in practice, given some pile of data, you can compute like the best trajectory. If you can perform this type of stitching with offline RL, and you'll get a better value trajectory than what anything was in the data set. Okay. Does that make sense so far? At least sounds great, right? Hopefully. All kind of hard to achieve, but at least sounds great so far. So no questions? Yeah. Like if it's Markov or without Markov. So like if we already had like the optimal trajectory is already in the data set, well then no stitching is needed yet. So it's so you're kind of in the lucky case where some expert has already given us the expert trajectory in order to be able to solve the task. It's just this, like in the real world, this we're rarely lucky enough to have like the expert trajectory. It's often like here's a pile of self-driving car data. Figure out like what are the shortest paths amongst all the like the start and goal locations that exist in this data without having to like specifically travel from every start to every goal that exists in the data set. So we're in some ways trying to be like more sample efficient with the data as well, like how much more can be extracted out of this. That's also a bit like more optimal in this data, but being able to do like that process more. And this isn't something that exists, at least in the normal version of supervised learning. They can't figure out how to directly stitch data, even if, so we'll, so that's where I'll get into like the next example to understand one of these details. And this is a bit challenging in order to be able to do. A lot of this also basically comes from the dynamic programming that we talked about. So if you remember, Q learning is based on being able to do dynamic programming, where like just given all the segments that exist like in this graph, propagate a bunch of information, and then you can kind of like just compute the shortest path through it because nothing is dependent across the different nodes. There is maybe one or two exceptions where you can go see some of like my recent work on figuring out how to stitch things together with using supervised learning. But basically, we borrow a lot of the ideas from RL, where it's basically figure out where things can stitch together and like add that stuff to the data set such that they exist. And that's sort of like, well, we're experts in RL, so we know the tricks in order to be able to make the stitching happen. We're just trying to get behavior cloning or like supervised learning to do this as well, because supervised learning is more stable, but it doesn't really provide the stitching behavior. So that's the benefit we get from Q learning, even if we have to go through the challenges of making it stable. Yes. Uh, it's possible, but you're definitely keying into one of the harder things to do. At least, like mathematically, like it's easier to stitch when we know the full state. So when we have an image, in that case, it's a partial observation. So because of the like details for the Markov property, stitching is at least, properly formed when we know all of the state information, and then we know whether or not things can be stitched together. So at least in your case, like in practice, it would certainly depend like how much maybe image history is needed to describe the full state, and then possibly being able to stitch things together like that. Although this is an area that people have been working on for a good while to figure it out. And if you want more details, kind of like that too, there's kind of like a sub area of this in like the robotics community that's basically trying to figure out how to go from images to a graph. It's kind of like doing SLAM. They're doing it, it's like a bit more explicit there, like what are the nodes inside of the environment the robot can actually travel from. This is at least internally, like hopefully the machine learning model will represent this graph and like where things can be connected. But there's a lot of work in the robotics community, like figuring out how to basically construct this from data and then just use that. So they're not really basing their work directly on reinforcement learning or Q learning. Um, It's possible, yeah. That one, I haven't seen too many papers try something like that. Like even if there is stuff in your data set and maybe your data set is so sparse, but maybe some other data set allowed you to at least train a model to imagine some trajectories and then use those for planning. So that could be one way to basically like add the trajectories into the data set that then Q learning can figure out how to stitch together. Uh, there might be some challenges though, like dealing with propagation error and depending on how your planning model works. And that is really similar. We didn't really do any planning for this paper, but it's a similar idea where we were just trying to figure out like clustering basically states to see if they were close enough, then it should be possible to like make a path through that state through two trajectories and they connect at some point. Yeah. So there's a lot of this problem can either be approached by trying to make Q learning more stable, which is not an easy ask, or essentially figuring out how to modify either your representation in supervised learning or your data set, such that now the data set contains all the possible like stitched behaviors from states to goals. So it can be done technically either way. The real question is which one of these is going to be easier. Uh, the community is still figuring that out. Depends on your preference. Great. Um, okay, so kind of related to this. So one of the ways to be able to do this and get convergence is to use model-based RL. We know this can be really efficient. The models can be trained with data from pretty much anywhere because it's really not based on RL at all or any of the assumptions or needs for RL. Um, and however, as we know a bit already, if we use some model-based RL method, it doesn't always perform that well. So like, great, it's training technically. It is actually being able to converge, but the problem is figuring out how to plan over long horizons. Because what the model thinks it's going to do, because we can just like roll out a trajectory and have it plan, looks great. It's very overconfident in itself. And then when we take that plan and like run it in the real world, this is the resulting motion that's actually achieved from the character. So even in this, like rewards and errors, sorry, creep in really quick, causes pretty bad behavior. So it's maybe if some can come along and help overcome some more of those issues for model-based planning, it could also be a good option here. Because then, like, just like your question, like you could use that model to generate data as well, since it's doing like state action next state to even generate some data and do some stitching. But for the moment, there's just always going to be this accumulation of error challenge for model-based RL. So there's some challenges to work over there. Um, but this kind of might ask a slightly different and kind of weird problem where Okay, well, maybe part of the problem was our model is only going current state, current action, next state. So that means like it has error propagation according to T, and how that builds. So what if instead we basically could train a model that takes in like the return that we want it to achieve and then the entire trajectory? Because then you could it's basically a supervised learning problem again. The input is just the current state, the return, because we have to have some data set of a whole bunch of trajectories, but we can compute the return on all those trajectories. So then in that case, we can basically have it as an input, like we want the policy to do this well for the algorithm right now. And then from there, it'll generate some trajectory. That trajectory should hopefully achieve that return. So now it's all a supervised learning problem. There's technically like no need for RL here. There won't be as much error because now the model is actually like learning to minimize error across the whole trajectory that'll be produced, and it should produce that return, plus or minus a little bit of error. Um, does that make sense? This is basically like train a model to have a bunch of different trajectories, and maybe this one is R1 or something like that, and this one achieves return 1, and then there's maybe another one that receives some return of 2. So then now we can just at this state do supervised learning with that data to predict the next of the trajectory. Okay. Is that clear? Sometimes a simple concept, sometimes a kind of weird concept to understand. Okay. I suppose this is kind of related to what you already did for homework 2, where it's like now predict some sequence of actions for the next, K steps, except for this one has now got the return as part of the input, not just the state. Okay. And then from this, an algorithm can basically be constructed. So this basically it produces a sequence of K actions for the next K steps in order to be able to achieve this return. And the idea is to be able to achieve this return to go that's being specified as the input. It's like one of the individual input features. And then this was used in the decision transformer paper. So now the idea as part of the input is the return, the state, and it seems like the action from the previous state. And then from this, figuring out, okay, what should be the next action that's predicted. And then overall, this model will basically learn to embed inside of it, like which actions to take in order to achieve certain returns. And there's just one kind of weird detail where, so now to figure out what the next action is, you kind of need to reduce the value of the return. So like whatever the reward was achieved by the agent, if you want the agent to stay along the same path in that next state, it can only get so much return. So you kind of subtract the previous reward and then follow that path from then on. Here, I'll show the algorithm as at least kind of explains these steps a bit better. So first, at least during training, interesting process, but basically sample a return. We don't know what is the distribution of returns that are even available in the environment. So basically pick them at random. And then from here, now the policy produces a state or produces an action with the state and return as input, and receive, some information from the actual environment. And this is what I mean by adjust the return. So now the return that will be inputted at the next state takes the return at the current state, subtract the reward that was achieved, because then basically the math adds up for like, it needs to properly be able to predict like the sum of rewards over the trajectory as it's unfolding itself into the environment. And then just include this return as part of the actual data when training the model. Okay. And then this is basically like just train the model to produce the correct action from that return and state in order to be able to achieve that. Okay. Questions? Maybe I'll give it a minute to sit and see if there are anything. This is probably one of the weirder algorithms that we'll talk about in the class. It really doesn't have very many, interesting properties for planning, but it can work. Good for now? I guess. Okay, great. Um, you're also welcome. Like, go check out the decision transformer paper or the many papers that followed it, where this can be used well. So, like, basically, part of the goal here is this is one possible way to achieve offline RL. This will converge. It's only using supervised learning. There's just a subtle detail where actually it might not be possible for this to do the stitching that we discussed because it doesn't rely on the Markov property and the way it can learn to put data together. And if you want some more details, you can go and check out this paper. Nope, not that paper. Not that one either. You can go and check out this paper where we basically prove that the decision transformer algorithm can't actually stitch things together. Okay, perfect timing. That should come back in a second. Um, okay, but there's one subtle detail, which I'm sure like everyone was paying very close attention to, but so the decision transformer, one of its other weaknesses, because of its like lack of strict properties, is, okay, how does it handle stochasticity? If now the outcome of taking some action is not deterministic, how does it actually figure out the following return for that, or even just the reward for that step? Um, so even with that algorithm, like exploration is kind of weird in terms of returns. Um, and you can basically just hopefully like put in the largest return and the algorithm might give back a lot of the details or basically the best plan. But getting back to the stochasticity, the because it's a supervised learning method, it doesn't really have any understanding of that there's supposed to be a stochastic planning problem going on. It doesn't actually have a way to deal with stochasticity. So like short answer to this question, if you know your problem has a lot of stochastic behavior, don't use a decision transformer. It's not going to be a great avenue there. Um, Luckily, though, there's been at least a couple of updates to this algorithm in order to make things more deal with some stochastic issues. But basically, the problem is some future states can be aliased in this particular learning problem, and it can't tell the difference between the two of them. So if there was some state the agent was at, and the agent was basically trying to figure out how to get the return to like add up to certain values where it's going to receive a return or sort of like a reward of one, technically it would treat either of these actions the same because either way, the probability of this one and selecting here gets a reward of one 100% of the time, even though this one only gets a reward of 150% of the time. When it gets that data from the next state, it's still just going to look like reward of one to it. So it's going to not be able to tell the difference between actually which one of these actions is better. But at least I know we're all fans of sequential decision-making problems in this room, very much. So we would definitely want to take like the action on the right that has like a stronger guarantee that the reward is going to be one without accidentally like 50% of the time ending up with a reward of -6. That one just doesn't happen to be recognized there. So you can go look at this data, or sorry, this paper here. There's certainly a couple of other examples in there of dealing with this challenge for decision transformers. And you know what? The the challenging or like maybe obvious truth becomes, okay, to do this, need to incorporate some more of the machinery from RL again into the training of decision transformer such that it can overcome this stochastic decision-making process. That's the whole point, like why RL was designed the way it is to overcome that problem, which captures like most of the types of decision problems to be made. And that's why we like its properties. We're just, often annoyed with how difficult it is to train. Okay. Does that make sense so far? Just remember, at least from this, we like RL because it is a proper solution and formulation to the stochastic decision-making problem. All right. Um, so those were at least some of the earlier challenges, and we're mostly talking about like mathematical frameworks a bit. Um, One of the other parts is like, so this model is training, like even for a decision transformer, it's collecting some data. It's a supervised learned model. It's hopefully going to collect some new data that's even better. And then that needs to be incorporated into the model. And this is like strongly connected to what we talked about in the last class, where, as learning occurs and as more distribution shift occurs, it's not always easy for that model to learn and incorporate in that new data. So the model hopefully should be able to adapt gracefully, continually learn, do these things. It's the type of learning that, in many cases, humans seem to do well, or at least a lot of people in the community seem to idealize people and their ability to learn. But also, as we get older, we seem to be less and less good at learning. But well, at least we're not all too old in this room yet, so we'll end up learning quite a bit. But even in model-based RL, there can be some of these learning problems, which was, so like the decision transformer is now a form of this model-based RL, where it's trying to incorporate more details into model-based RL. But if this model is now trained over some pile of data, and the paradigm that's growing the community a lot is like train over a big pile of data, and then in the future, there'll probably be something to fine tune. And the idea is to make more of like a foundational model or it's like something that'll be more reusable from this. So then short story is, even one of the concepts that's supposed to be the most generalizable, because in model-based RL, it's just a forward model that takes state, action, predicts next state, and reward. Doesn't matter what policy that data came from, doesn't matter what the goal is. Still, even with that model, because you have to remember, like in the loss for training the model, it's an expectation over some data distribution. And if that data distribution changes, then that loss is not really as guaranteed as it was before. And in this case, it can pretty obviously been shown that, once the task or the distribution changes even a little bit for a kind of simple task, even the model-based R algorithm basically suffers from a lot of plasticity challenges, gets stuck here quite a bit. And this is unfortunately something the community is going to have to spend a hard time thinking about, like how to design these algorithms, how to design these neural architectures such that when the data distribution changes, and because it changes more for RL problems than it typically does for language problems, how to overcome these changes. Okay, does that make sense? This is sort of like, we've talked about offline RL for a bit, but I want people to keep in mind that offline RL is sort of the first step in an algorithm that will become fine-tuned. So it's sort of like extract the most from the data, then we'll run RL on this. And it is actually unreasonably challenging to figure out how to do good RL even after pre-training some policy. We'll talk about this more and more in the class now that we're kind of covered a lot of the methods that could be used to pre-train some type of model. Okay. So let's talk about what actually is offline learning. So basically, now instead of doing this model-based RL, which already seems to have some challenges in terms of long-term planning and some challenges in plasticity, how can we train Q functions to be able to learn from all these certs, basically collections of data? Basically, one of the challenges is like normally this diverges. In fact, most of the time, as the data becomes more diverse and kind of more different from the actual policy that's currently collecting data in the environment, the likelihood of divergence increases. But off policy, because it always needs this on policy data, because basically the Q function is an estimate over Q values dependent on some current distribution for some policy. And as always, this is at least like always theoretically true, independent of any deep learning coming into the mix. But then also our good old friend, the deadly triad, that is basically always going to challenge us from having a really good time where we can get everything we want and be able to have a really great algorithm. But anytime we do that, things diverge. So just as a bit of a reminder, so for the deadly triad, this was just like bootstrapping can cause a bit of an issue because the model and algorithm can bootstrap onto itself. There's also function approximation. So after some update is performed, like the output of the network can have slightly uncontrolled values that can't be accounted for very well. And then there's still the off policy part, like being able to train from all data. And then basically what we're going to talk about now for handling offline RL is like one of these problems is going to be tackled very specifically in a way in order to be able to enable offline RL training. Okay. And this is like part of what I was mentioning a bit. So this is for the function approximation space. One of the challenges, okay, there can be unbounded Q values with any big giant nonlinear model. And you can see that this causes even more issues with divergence. So if some max overall Q values basically follows this is an interesting plot that shows the distribution of like, it's kind of like a histogram there where if something is wider, basically more values for the Q network or more like that number. So this actually shows that there can be a large change in distribution of the possible outputs. The kind of same over for here. And I believe this is like a large versus a small network. So as the network gets a bit more large, things get a bit more out of hand in terms of possible outputs that'll come out of the network. Okay. And as we've talked before, so some ways to start to overcome a few of the challenges of the deadly triad is like use end step returns, because then things are more on policy, less off policy. Then or yeah, using some larger network leads to some type of divergence. And these also directly correspond, even though like this is looking at the Q values right now, not necessarily the policy, but these really very tightly correspond to the performance of the agent. As all these bad things are happening, so does this degrade the agent's actual performance. Okay. All right. So then this kind of asks this question, okay, how can this divergence be prevented? What causes this divergence is really the real question. And you know what? The reason algorithms and us basically sometimes start to diverge, a lack of support. So maybe it could be a good time to like rely on some of the other things around you, some of the other data sets, something like that, in order to be able to provide some support. So this is where basically an offline RL, like normal reinforcement learning is, collect some data from the environment, train it on your actual algorithm, and interact in the environment some more. And this is where offline RL is basically some process collects some data. It doesn't even have to be expert data. And in fact, most data sets, like the stuff we're using for OG Bench, not expert data. It's just some amount of data from that. And we still want to be able to train a policy that'll learn from that data. And then just train over this many, many times. And then hopefully this last step is now be able to deploy this in some new environment, maybe collect a little bit more data, adapt quickly, and be able to be an expert at that task. Okay, does that make sense? I feel like we're all a bit more familiar with this because we spent a while going over behavior cloning, where it's like, here's a data set, do well on it. But now here's a data set. It's also labeled with rewards. So can we train a Q function and a policy from this? Okay. So then a little bit of this comparison to get into the details for, okay, like what is going wrong? What is the thing that's causing real issues here? Not just it's diverging. What is one of the things that we can control? So in this comparison, where an offline RL, more data is going to be collected, more on policy data is going to be collected. Then offline RL is basically this one data set. There really becomes this challenge. There's some data set here that's been collected in the environment. We don't have access to what that policy was, but there's some distribution kind of embedded into that data set that is this particular object. Okay. So we haven't talked about this, at least directly, in terms of how to define this object. But this D here is often described as like, basically, this is the distribution of states the policy currently visits. Sometimes it's discounted, sometimes it isn't, but it's this object that just basically says, given the current policy or parameter settings, like this determines like the probability of just visiting any state in the environment. If you were to like unroll and run that policy off into infinity. Okay. And this is needed for like performing some of the expectations, like the expectations in the mathematics for training these models. And it's because this thing is dependent on this particular policy, what's at least sometimes referred to as the data collection policy or the behavior policy. And to be honest, we just don't know this. Even if there's some data set that's been collected, often the data set, doesn't cover the whole space. It hasn't been run into infinity, so there's no way to be able to model this perfectly. But that's a challenge because basically from this, these two other components need to be like computed or like understood in terms of the distribution for the agent. Because in those cases, the state that we end up wanting to like do this argmax over in order to be able to find these parameters now depends on basically knowing what that policy is, what that behavior policy was. And now this is the part of the problem for why like even being more off policy in an off policy algorithm, not an offline one, causes divergence. It's because basically somewhere in the data, but we don't have that policy anymore, but it's estimating, what was that behavior policy that generated this data? And only if we know that can we actually construct a Q value that can like make sense with the data. Okay, does that make sense? This is always like, maybe you can always think of this as like if you're playing a game with like a friend or a family member, and you're trying to understand why they do things. And maybe you think about this more or less than I do on an average day, where I'm trying to understand why people do things the way they do. But I won't actually ever know that because I would need to know like their exact behavior policy, why they made those choices. And their policy comes from a wonderfully beautiful lifetime of experience that they have, and that determines that, and it's different from my experience. So I can't, I'll never be able to totally understand why other people make the decisions they make. This seems to be more apparent these days, it seems, but it's a whole different conversation. But does that basically make sense? Like even if you're trying to estimate and trying to look at like, I don't know, all the stuff I do here in the class and like wave my hands and why I do it, you still couldn't really model that behavior. Not unless like you somehow had access to like all of my prior information and my actual policy, then you can try and construct like the best Q function from all the stuff Glenn did. But you don't get to have access to my brain. It's probably a good thing. And to be honest, I think is a pretty important part for maintaining humanity. But that's a whole different conversation at the moment. But hopefully that makes a bit more sense, kind of like figuratively rather than mathematically. Okay. So in this case, and remember, we're going to be training our policies now from these Q functions. So if there's some limited data set and we basically run an algorithm to fit our Q function to that data set, a very similar thing happens to that like figure we saw earlier of like the humanoid on the left and the humanoid on the right of it doing like overestimating itself. So the Q values as well will start to like really overestimate their actual behavior. If we just run like just off policy RL and have it train over some data set. So it's not quite training a policy yet, so it's not going to bootstrap so terribly. But unsurprisingly, when some agent trains over only its own data, doesn't get any feedback from anywhere else, it just tends to think really highly of itself. So in order to actually understand if you have a good policy, it needs some other mechanism to come in there and correct it, give it feedback, not have it overinflate its understanding of actions it's never taken in the world, in states it's never been to. And this is where the performance basically comes in. It's like, okay, now running that policy in the real world is really terrible. Far from at least its predictions about how well it was going to perform in the world. Okay, does that make sense? So this is already starting to become a little bit of a problem because of overestimation, even from the original data, which we've discussed a bit before. Okay, so then what's the cause of this? So one way to look at this is basically the network is going to be overconfident because there is very little support. And remember, support here is that mathematical term of like, is there data in the data set that basically covers where that prediction is going to be made? And in the case for RL, it's very often that this, isn't actually going to exist, especially for offline RL. Like some data set has been given, it's going to cover some amount of area, but then the policy can still be asked to like predict in states that don't, like we're never in the data set. That's kind of one of the normal problems. But there's a variation on this problem now for RL. If you look at this, like the x-axis here is not states, it's actions. So even if the data set contained a state for like this room right now, it it doesn't actually happen to contain all of the actions to be taken from that particular state. And in that case, because there's no support over all those other actions, the Q function will likely overestimate, or at least can overestimate what's going to happen for taking those other actions. So like, for example, right now, I don't know, I've never tried to do a backflip while teaching, but I can overestimate and think like, it'll probably be perfect. Nothing will go wrong. It'll just be a normal day and nothing will ever change. But, I've got no support in that area. So I'm kind of guessing at the moment. And so it's, you know, more or less, it's not going to probably turn out well if I'm trying to like estimate my performance over those actions I've never taken. So the idea, at least for this first offline RL algorithm, is basically be a bit more conservative. So if it's possible to compute like from the data set doesn't have actions in it for these other values it's trying to predict over. Basically, like be conservative. Basically, push down the values, the Q values for all of the actions for specific states where there isn't actually support in the data set. And this basically says, okay, if you don't know anything about that area, just assume you do terribly, like a good person should. If you're not an actual expert in the area, you should probably not try to speak like you're an expert in the area, something like that. Okay. And this is where, at least, in the conservative Q learning paper, basically this balance of objectives is used to be able to do this learning. So there's one objective so this is minimizing the Q values. So this will help like push down some of the values where there isn't always actions that exist. However, like the whole goal is to maximize the Q values under this B. So if you're looking at the papers, this B is this is the behavior policy. This is the thing that we don't have access to, but we want to maximize the Q values that we suspect there is support for that behavior policy. And then this is just the normal Bellman error in order to be able to do updates and train the actual Q function. So it's really just these two processes, like do updates, try to maximize stuff in support, and then you can do some minimization for some other states that are only coming out of the policy, but they're not really in the data set. Okay. Does that make sense? No questions? All good? Now's a good time. This will basically be part of homework 3, so it's totally clear. Not that I won't answer questions in the future, but now is always a good time. All right. Well, we'll go into a few papers like this too. So I think we'll probably like get some more ideas and some things that don't seem quite so clear out of this. Okay. How are we doing? All right. All right, so let's stop here and take a break because this is sort of like we've gotten to one of the offline RL algorithms, and now the rest of this is like variations on offline RL algorithms because this has still many corner cases it doesn't perform well on. What is it? It's 153. Let's start again at 203. Mhm. All right. Sure. Like that B. Yeah. So it's called like the Bellman operator. So um, it helps me be able to fit this equation across the slide mostly, but it's basically just our Bellman update that we've talked about for Q learning. But often if you go look at like Q learning papers that are more on the theory side for Q learning, they're going to use this notation, which is just the Bellman operator that says, if you apply the Bellman operator to this, it gives you that new version of the Q function that's been updated, and then you minimize the error between those. Mhm. Yeah. Um, mhm. Okay. Yeah, I mean, we can start with the intro related work and preliminaries, and then this will be, I mean, preliminaries and a bit of the methods. Mhm. Mhm. So this is, yeah, so like for Friday, now that you've got the proposal, and the proposal is like writing a slight version of the introduction. So then the next part is really like related work and preliminaries and some of the method to understand at least like what type of method people are going to start using. And that's it. It's not really experiments yet, but if you've got them, you can start putting them in there. So then at least I can give you some feedback on them. But I won't be grading that point. Or you can just like send them to me like in the project channels that I created for everybody. So I can give more advice on like what may or may not work a little bit better for the type of things people are doing now. Right. Yeah. Mhm. Yeah, that's fine. You don't put much work into getting PPO to work either. Like focus on your project. PPO is kind of like debugging just to know that like if your thing is working, it should do something like similar to the performance of PPO. It can work well, actually. It just often takes a lot of data. Sounds okay for now. I might ask a few more details about this later, in terms of how to understand this. So like you mean you'd give the policy the initial state and then like the goal for like what would be the final configuration. And then it has to figure out how to transform the world into this. Mhm. Mhm. By the whole project, you mean more like the starting from the image and then going right to the final solution. Mhm. Well, yeah, I mean, you can try that one for PPO. I mean, I would say like try to shoot for that final project. But I think in terms of getting there, you first need to like, yeah, break it up into these sub like goals, get those to work. Just so you know, like policy training works. You don't need more data. You know how long it takes to train to solve that. And then you can start maybe like putting two steps together, something like that, and then trying to train something that handles those two steps. And you'll see if you can get far enough to training a model that covers like all the steps for doing what is kind of like your like block stacking assembly task. Yeah, it's true. A lot of algorithms kind of split this problem apart too. Like there's one thing that'll do like the block stacking, it's just figuring how to move all the stuff. And then another policy that's just sort of like has been trained over a great variety of like moving a single object to a location. So it just kind of like takes commands of moving objects around. And that might be a way to separate it, if that makes sense. But I do encourage like kind of start small, make a couple of milestones for trying to make this leading towards the what you call the full project, but it's like the full hard problem. Yeah. Hmm. Maybe. But do just remember, you're kind of like graded on what you learn from the class and what you show you've learned. So this would be like, well, you'll probably get PPO working, but it already sounds like you're considering like how to get your algorithm be able to do like the image processing, do the learning and the construction, which is all stuff from the class. Okay. Yeah. Yeah, yeah, it's been around for a little while. The hyperparameters sometimes need to be changed. Yeah, stable baselines is actually getting a bit old, but no, don't implement your own PPO. If it comes to the baseline, do not implement that yourself. Focus on implementing the thing like that you're proposing in your project. And just like find some baseline that's just more of like it's an indicator of like how hard this problem is. Because like if you, it's unlikely to happen, but like if you take PPO and then run it on like the full hard problem and it works, that's not going to happen. But that would mean like, okay, well, that's the level of how much data and time is going to be needed, and then you can try and do better than that. Yeah. So it's just like it's an approximate indicator of like, well, this is how well the community's RL algorithm performs. Can you do better than that? And like, what do you change so you've got like better structure or whatever, such that it can like be able to learn faster. Mhm. Okay, well, maybe I'll send her a message right now. But because I don't know if the Panda one supports the exact same arm. Part of the problem with that Viper arm is there's like 5 or 6 versions that all look similar, but they all have a slightly different number of joints. For the Panda arm? So is this a different arm or just a different simulator? Yeah, okay. Maybe in the channel for your group in the Discord, like share the simulator that you're thinking about using. I can at least look at it because we've got one already and we already like built an interface at least for that arm. Yeah. Yeah. Sure. Hmm. Oh, shoot. Okay. All right, everybody, let's get back to offline RL. I'm sure we're all waiting impatiently to get to some of the other algorithms, which maybe hopefully are easier to code. Um, they're not, but at least there are definitely some other options. And just waiting for that signal to come back. Okay. Is anyone epileptic in the class? I'm hopefully not like trying to kill anybody right now from this, but okay, things are all right. Okay, so this was basically one of the ideas to be able to do offline RL. So this should like, it can train a policy, it does converge, gives an okay performance over time, and it doesn't overinflate its values for actions that are outside of the support of the data set for the most part. But there's actually been a couple of improvements on this algorithm. But there's actually a slightly like a different way we can think about this problem. They're like, this problem still always exists. The fact that there's some action support. Here, this particular objective is trying to combine some terms to basically, maximize stuff in support, minimize stuff out of support. But there is a slightly, like even more explicit way of being able to solve this problem. And this is what's done in batch constrained reinforcement learning. If basically, if this is the problem, like the problem is basically backing up over actions, like computing some max over actions that aren't in the data set, then let's just have the algorithm never do that. Seems kind of obvious, but it's basically this problem. If the policy is supposed to be pi over argmax for A, but only like with this constraint, such that that S of A pair is actually in the data set, then it's fine. Like the policy will not suggest any action for something that is never taken in the actual world. Makes sense, right? And there's just a few details on how to actually get this to like be an actual algorithm and not just a conceptual, like this sounds correct for now. So actually, because this argmax is over any action that's not from the data set, then we can actually just change this argmax a little bit. So now it's going to be argmax over some policy. And this is really just a probability distribution given some state, output, and action. The difference is this is a slightly different policy than what we've talked about. This is just a policy that's trained over the data set. So now this policy here, it's not like the optimal policy, nothing like that. It's literally just, here's the probability distribution over actions and states that appear in the data set. This is like exactly what we wanted up here. The top part is like a such that, so it sounds like a hard constraint. And now here's sort of like our soft version, like over the probability of this action actually existing in the data set. And then basically for anything that's not in the data set, it should predict a 0 because it never saw anything like that. Yeah, does it make sense? This almost makes a bit like almost too much intuitive sense. Like, great, now we can learn a model that is the data set. Don't do the argmax over anything, only do it over something like this. That's now at least some probability measure over stuff that was in the data. The nice part is this can actually work pretty well. And now there's just a bit of a trade-off between these two algorithms, so we can have this discussion for a bit. So there's kind of like, there's this goal for like making one Q function. It's a balancing of a couple of terms, and we haven't talked about that part much because here, you know, there's at least like I mean, this is only a learning value over here, or a learning parameter, but there's still some way that these objectives need to be weighted, which is sometimes a bit finicky for offline RL algorithms in order to get good performance. At least, and then there's a trade-off here where this method So there's less hyperparameters, but now the problem is an entire another network needs to be trained. This is the thing that's going to estimate this probability distribution. So there's kind of a trade-off between these two, and sometimes you might select one over the other. Uh, I mean, certainly, if there's not a lot of data, it's really hard to do the one on the bottom. Usually takes a good amount of data to train like some generative model that'll kind of basically understand the probability distribution over actions. So there's a bit of a challenge there. So it's kind of if you prefer spending your time figuring out how to adjust some hyperparameters across losses, and I know some of us, a fair bit of us in this room probably do this a bit already, and we know it's a bit of a pain, or you can go with like this one where, well, now the time is just spent like learning how to train this model. And once that's good, you can kind of fix that. And that can work pretty well over time. Okay, does that make sense? We'll get into a few more details here, but so now that's maybe, hopefully I haven't made it sound too easy, but there's certainly some details about being able to train this model. Some action distributions are crazy and wild. So sometimes if you look at that distribution, and for example, like this one would usually work a little bit better when the action distribution is less multimodal. Because here, if it's doing this estimation, there's still a lot of expectations here. They kind of don't capture the modes very well. This one could maybe capture multimodal behaviors in the data set better, but it does require us like being good at programming algorithms for these types of distributions. So I'm basically going to give one example of this. So one would be, okay, what is that distribution going to be that's sampling here? And there's a couple of different methods that could be used. So this is much more similar to that behavior policy, which we're basically trying to estimate directly. Where if this is the ground truth data set, maybe it'll be better to like use a diffusion model. A diffusion model is better at estimating like distributions, capturing different modes better, at least better than using a VAE for this. So if you have some information or intuition about your data, if it's really highly multimodal, and if you're using this like batch constrained method, look into using something like a diffusion model, something that'll capture this really well. Maybe something like a transformer model if your distribution is discrete and really complex, because that will help basically perform a better max overall actions that'll actually fit the behavior distribution better. And at least here, because this first paper, they used a VAE to capture this distribution, so it worked, but it didn't always give the highest performance because VAEs, they have a hard time capturing different modes. This particular one, just kind of, if these were different actions, where this is a tea kettle and a knob for a stove and a microwave, and basically the data set has trajectories to each of these three particular locations for tasks to solve. Then a VAE kind of just makes this Gaussian blob in the middle that doesn't really separate these data sets very well. So it's not capturing the behavior distribution strongly. Okay, does that make sense? It's always, if you've got some intuition about your data, use a bit of that intuition to pick your hypothesis and model class a bit better here. Okay. And then one of the subtle but interesting parts, which we've talked about a bit, is sort of like, it's not always easy to see this multimodal behavior in your data set. Like if you just look at actions and like remove the state from them, they basically all just blend together into like actions. Any type of action can happen almost any type of state wherever. So it looks like this all covers really well. The important part is to actually look at, what are plans, like at least sequences, because then behaviors start to look like they've got more modes that go across different areas. So one of the pieces of work that we did was now, okay, instead of looking at just the individual action distribution, if more modes start to appear in the data set, then we can capture them better, but they only appear over the data set if we essentially predict the next H actions here. So something like that. So at 5, barely starting to see more than one mode in the data set, but once a model that basically It's kind of like, no, pi, a from, like 0 to h, given some state at t. I guess this would be t to h plus t. Then basically, once this model starts to get this, now there's actually some modes that start to occur inside of this data, and those can be captured better. And also, as I just discussed with some people too, this also makes the control a bit more hierarchical. It also basically does a form of that action chunking that we've talked about and you did for homework too, that actually helps the model have some more consistent behavior. So just keep this in mind. This is kind of like a interesting / complex comment on understanding how to look at distributions when you get temporal data and what it means to have multiple modes. And then basically being able to instead train a policy that isn't this, but is essentially I of a from t, I guess, t plus h, given some z. And now z is basically kind of encoding, the distribution that's been seen so far. Now this is kind of like, you kind of key into one of these modes to identify, okay, now the state says this is the mode they occur in, follow this policy for the next h steps over this. Okay, does that make sense? Somewhat here. Basically, one of the parts that isn't quite, at least included here, just out of details, is we still need to train some diffusion model to basically predict over the length h. So basically, all these steps, 8 or 20 steps, can be boiled down into some latent variable, and now your policy is actually trying to specify these latent variables the other way around. So there's kind of a two-step process in here. Essentially, this other diffusion model is trying to capture short plans, and then from those plans figure out how to plan over those, or at least short sequences, and then from those figuring out how to select them. And then the modes occur more naturally in those chunks. Okay. And then at least for offline RL, this tends to improve performance quite a bit. Okay, but the challenge is this method still definitely runs into that problem of it being a combination of many models. So it's sometimes really tricky to get these all to line up. So now this algorithm has to start out. First, it has to train a diffusion model to represent segments. And then from that, it can train a policy. And then from that, it can get the Q function training. So there's at least 3 different models going on here. It's all a bit challenging to keep these all playing well together. And if you want to run a new experiment, you might have to train all these different models together. So it sometimes takes a little while to train. And if you change anything about a prior model that this builds on, you have to start over. So there's kind of engineering challenges in order to achieve some of these models and build on this type of method. And this is almost one of the reasons why we kind of prefer doing large foundational models, is hopefully we can just kind of let the model take care of some of these extra steps and engineering challenges in a more graceful way than trying to do tons of hyperparameters and weird engineering to get it to work. Okay. Okay, but still overall, there's still a lot of, the deadly triad still exists. And basically some of these algorithms kind of overcome these issues. So for here, the 2 methods that we really talked about for CQL or the batch constrained learning, they're kind of overcoming part of not really the bootstrapping, but more of the off policy part. So it's training from other policies, but it's got a better estimate to make sure it's not bootstrapping over out of distribution actions that are in the support. So that helps it not diverge. The other ones we've kind of talked about for a bit for function approximation was a lot about what we talked about last week, use things like layer norm, maybe resets to condition the overall network so it has a smoother behavior, doesn't end up overfitting or have really large changes in its outputs. And bootstrapping is still always going to be a challenge, but that's why target networks are often used, even though they have their own problems. Okay. Yeah, all right. Okay, so good. Now we're going to get into some examples. So that's kind of the foundational part, and now this is going to be, okay. Maybe that's more like the groundwork, and I'll be careful about the use of foundational in the class since it's sort of like half of our topics. But now this is basically what is on the edge of what people are trying to use these algorithms for right now. So we're going to talk for a bit about being able to scaling Q-learning to transformers. So if we want to now have a Q, like basically doing offline RL with a Q function over a really large amount of data, possibly multimodal data that's inputted, how can we get that to work? And then basically kind of like getting back to the point where if everyone kind of remembers, like why do we want foundational models? Because we want fine, yeah, go ahead. Yeah. Which is kind of odd, like occasionally, like if you squint a bit and think about all the language model companies these days, most of them are like zero shot transfer. It's like, great, here, answer this query. I know I'll kind of like ignore a little bit of the test time compute stuff that's been showing up a lot more in the last few months. But part of the idea for a foundational model was not really this zero shot transfer idea. It's sort of like, what was all the evolution that happened to make like biological things be able to do well in their environments? They're kind of like really pre-programmed to do well in a very specific environment. So then how do we make something like that for an agent that can then adapt really well in the real world? So we're going to basically return to this a bit now for these last two papers. That's now partly is offline RL like a better option to be able to do this pre-training such that fine-tuning will be easier? And a little bit about how to actually achieve this fine-tuning because it's still a bit weird, especially when it comes to RL. So let's get into some of the details. So the first one is for basically being able to scale to like a really large transformer. So here, there's basically this paradigm. There's some human demonstrations. So there were some people that either like sat down at a desk with a lot of patients and then would like teleoperate this robot for a while, which we've talked about. And then now there's going to be some amount of autonomous data that's collected. And the idea is like a better policy will be achieved in a shorter amount of data, given some pre-training on the pile of green stuff, and then a little bit of autonomous training in the real world. So this is part of this kind of like pre-training step fine-tuning chunk. The pieces that end up being helpful and that are a bit interesting. So like one of them is doing autoregressive Q-learning. So if you remember, like a transformer is autoregressive. It's going to output tokens. But so it might at least seem like good first way of doing this is, okay, I could just output a whole bunch of Q values for that current state. All right, how do you do this in a continuous space when you've got multiple dimensions for your actions? It starts to get kind of weird and complicated because now like your transformer is going to have some challenges and you really don't want to kind of enumerate a whole another transformer that ends up being input for this transformer because then they actually just don't play very well together. But they've got a really unique kind of method in order to be able to overcome this. And they basically convert this problem into another autoregressive problem that I'll show more on the next slide. This is basically what we've talked about. That's like conservative Q learning already. So use that for training. And always this recipe, slightly better performance if you can get some online data. So then what do I mean by this autoregressive part, which is a little bit tricky, but basically what they did in the paper is they discretized the continuous action space such that there were, this many bins for any actual continuous value. And now basically for any state, this particular model would output, a number of like autoregressive steps according to the number of dimensions for the action space. So now this is basically a Q value per action that's available to the agent. And then at the end of this, it can basically perform now a different type of like actually trying to get this to match. So like this will basically output a bunch of Q values for each action, compute basically a Bellman update over all of those, and then be able to train each of those predictions for each action to actually be a Q value for each one of them. So this is an interesting way in order to be able to encode like putting this into a Q function, or sorry, like a transformer, and still being able to do a lot of the like larger scale training even for a Q function, or sorry, for a transformer. Uh, okay, does that make sense? This is it is definitely a weird network design, that's for sure. And there's probably other ways to do this, but the unfortunate pain point is like transformers, they output discrete objects. Like there's a tokenization. So like how do you make use of that? Because if we want to be successful, we really can't change the transformer training recipe too much. So then how is it really do we fit our normal like RL Q function training problem into the transformers design and then still be successful? Mhm. Okay. No questions? This sounds like totally makes sense. Would have been the first thing that you might have tried if you were trying to get this to work. Can't quite see it on the paper. I doubt it'd be the first thing anyone would try. There's like 30 authors on this paper, so they must have tried like 30 different things, I'd guess. At least everyone gets to give one try in the actual paper before kind of like ending up in this architecture design. And at least in the nice part, this does scale kind of well. So at least this is doing offline training over something like the OpenX embodiment dataset. It's a little earlier than that, but it can get some pretty good performance from even just that data set in some tasks. And then at least always kind of as like a way to make sure things don't get too off track, there's some Monte Carlo rollouts as well, since there's information known, even though it's like reward after every action is predicted and then being able to do some update. So certainly some details here. Yeah, I mean, if you want to know even more, although the paper could have more details about how this works, you can go and check out, uh, yeah, this Q transformer paper that was a paper at Coral, I think 2 years ago. Okay. So then if there aren't any, so okay, sorry. So there are some details about being able to get this to work, of course. It's not just that design. The design worked okay, but then there was also a bit of like how to actually like train the loss function at the end of this transformer. So here, basically after, this is like with and without, so pay a little bit of attention to those words. So if this was just using like softmax without using this like autoregressive version of being able to do predictions for rewards, it doesn't work nearly as well. And then basically if any Monte Carlo or this conservatism is removed, then this doesn't perform well at all. So it needs this particular combination, especially having the conservative and Monte Carloism combined. And that ends up achieving some good performance. Okay. All right. Okay. Does that make sense? A bit more? Okay. Because now we're going to get into the slightly weirder stuff, but there's at least some more interesting things to discuss. So this is an interesting thought. Let's play a little thought experiment for now. If you were doing online learning and I don't know, somewhere on the internet, there was some data that already existed for your current task and same reward function. Do you think it'd be possible to use that data to try and accelerate like your online training policy? It's at least non-random data, I'll say that way. Like it's could be somewhat useful, but it's nothing that's currently come from your current policy. So then how can we maybe go about using that data? Any thoughts? Give it some examples. Sorry, can you say that a bit louder? I'm having a hard time over the air conditioning. And so what do you mean by use it first? Just to double check. hmm I mean like offline RL pre-training or behavior cloning pre-training. There's a lot of pre-training has now got like 3 definitions so far in this class. Either one. Okay. I know you've got a preference for RL too, so yeah, makes sense. Um, but so that could be a good start. But that'll be the second paper we'll talk about. So this is the first one that has a slightly different way of doing this. And here, the idea is literally if you're going to start from offline learning, and if you remember from some of the prior like algorithm papers we were talking about, like for DQN, the replay buffer size grows to 1 million after it's finally collected that much. What if we just like initialize the replay buffer with like 1 million from that expert data, and then just ran online RL from there? It's like, and cross our fingers that that'll work really well. It should at least give like some better bootstrapping. Like if I don't know, a biological agent suddenly started out with a memory full of all the expert stuff from how well they do, like from some other experts that could help. And then so like basically this paper is exploring this concept, like how can, for just online RL, so there's no pre-training here, that'll be the next work, how can just like that data set be used? And even to just sort of like inflate or improve the online training process. So it's a bit of an odd concept because we haven't really talked about it, but it also sounds like kind of a creative and good idea. Just like put good data in the data set beforehand in the replay buffer. And then when the replay buffer is doing experience replay, hopefully we're bootstrapping to great Q values. The challenge is basically a lot of the stuff that we talked about in the last class basically just says like, no, you're not allowed to do this. This is going to cause divergence. And the algorithm just kind of like dislikes every part of this idea from like a statistical and gradient. I think oh, okay, that was more of a Wi-Fi issue that time. But I think this is still gonna work. Come on. Hmm, it's not what I had in mind. Okay, this is still good. It's still recording. And then let me just go back to the slides, hopefully. It is not still recording perfectly though. Okay, now we're good. All right, thanks for your quick patience. So basically, like this could be explored. So like using some version of SAC, and basically let's start out with this concept where, okay, so it might not work the best to just like dump all this data into the current data set for the algorithm and then let it train. In this algorithm, they've got this symmetric sampling process. So there's basically one replay buffer with this offline data, and then one replay buffer with the stuff that's learning online. And then from here, the algorithm will sample 50% from these two batches of data. And then from this starts to look like it can perform well. So here, this is with the symmetric sampling process. Uh, Looks like maybe something was actually missing from the paper and the legend. But basically, this is one way to be able to incorporate in the data and then actually be able to get the training process to work okay. And then there is this extra detail, though, of uh, basically there's always this challenge of, if something is trained on some offline pile of data and then transferred even to some new task, these are kind of like two different distributions. The model is not necessarily going to like these distributions, the fact that there's two of them if they're not similar enough. In fact, the model can end up like really overfitting the two of these and they kind of ignore each other and don't help each other at all. So they need to like overlap by some amount. But one of the other parts that ends up being really helpful, and which we've actually kind of like introduced almost too many times, I feel like 20 papers discovered this in the same 3 months last year, but like using layer norm is really helpful again in this case. So that ends up being, yeah, okay. Yeah, so like use layer norm in this case because it kind of adjusts the loss landscape again. So if there's some data here that looks like a cone, And that's very specifically chosen geometry, but it's at least good for here. So if there's no layer norm, and like the loss landscape just kind of like extends out from this cone and can get really, really big over time, or space. But layer norm kind of like flattens out the edges of this cone. So it looks more like a traffic cone than it does actually like an ice cream cone, if that makes more sense. So we live in Montreal. We like and we are familiar with traffic cones. It is at least not currently the season for ice cream cones, unfortunately. Although there's like one or two places in the city that still serve ice cream. They're really hard to find. But anyway, but this is so like this loss landscape helps again, because basically now if we're getting into the problem of mixing data sets of different distributions, we need to pay really close attention to like the loss landscape and the differences between these distributions. Otherwise, the model is not going to like any kind of the combinations that are going to be performed. So then here, this ends up helping quite a bit. So both of these all have like the layer norm added. Maybe I'll zoom into this for a bit. But also that, so now some offline data can be used and basically incorporated into the symmetric training process. It is a bit important how much data is used, like the percentage. So here, if only offline RL data is used, great. Maybe the policy is good at the data distribution in that offline data, but not on the current task. So it's not picking up any online data. And then if basically no offline data is used, okay, it learns like it would any on policy algorithm, but so like doesn't get to take advantage of that offline data to at least be able to do some bootstrapping, some learning. And this is a bit of a balance. It's also like not one of the ugliest hyperparameters to tune, so it's not too challenging in terms of like coding and being able to reuse overall. Okay, does that make sense? This is kind of like it's a simple concept, but like with deep RL, any simple concept actually ends up being kind of tricky to get working just because like deep RL doesn't like basically things happening where it's not just like, let's do on policy training. That's the thing that kind of like works a little bit more, but that's also like the most sample inefficient thing. So now if we've got some data set, and for many problems, we have some amount of like data already available. How can we start to like include that into even the on policy training process to make them faster? Okay. Any questions so far? Okay. Just kind of like think about this concept a bit. This is, I guess we're going to get into the next part in a second. Okay. So there's always like a few other regularizers that end up helping. So dropout, it helps a little bit, but mostly what ends up helping is also an ensemble of critics. So we also saw this a little bit last time as well, where in order to like avoid some overfitting and basically some overestimation, take an ensemble of critics. So in this case, I think, no, I don't quite remember the details in the paper. There's, I think, 5 to 10 basically versions of the critic function. And then those are all trained over like the offline data set and the new data. And then using an ensemble method over all of these helps us perform better and not end up kind of like overfitting, overestimating itself. Okay. So this is called RLPD. Basically, this provides for some nice design considerations. So like if you've got some online RL problem, but you've also got some data set available, what are the best kind of levers to adjust a little bit in order to be able to make use of that offline data? As always, like the details are a bit important in order to be able to get the most out of that offline data. But just remember, this is still well aligned with that goal, like that goal of basically figuring out how to accelerate online training. Because there's sort of two ways to always think about this in our community. It could be like, sure, great foundational model, but we also care about the data. So sometimes you can either try to improve your training if you've got some data available directly, or you can try to improve some training from a model. Depends on your preference sometimes, because basically the data is what is important. It's got all the information in it. Training a big model can be helpful to some extent, but it depends sometimes on goals. Sometimes our big giant models are incredibly slow and we only need some specific data. And sometimes there's a balance between these two. And that's really what the next kind of step is about in this algorithm. Okay, but does that make sense? Any questions? Still pretty good. Um, hmm. So this is still all like focusing on like TD3 type algorithms. So like basically whenever we're doing this like foundational model training stuff, it's almost always for something like TD3, Q-learning, or SAC, some off-policy algorithm. It's the only space that we can really do like offline RL training. PPO, not going to really work well in this area. That's for sure. At least it certainly doesn't have the option to learn from off-policy data very well. So it does mean if you're interested in the area of doing foundational models, having things being more sample efficient, we've got to start to become better at making like off-policy algorithms. So get familiar with like TD3, SAC, and the many ways people try to like bend these and adapt them such that they will work pretty well for being like sample efficient on some new task, something like that. Okay. All right. So then this kind of, we'll go back to kind of like the other concept where now this is, okay, so like understanding how to be able to train these models. And now this is more of the foundational model way. So if there's a big pile of data, train it over, basically use offline RL to be able to train a model over this pile of data. But then we still have this question, all right, what should we do in the fine tuning process? How do we achieve the best performance? But yeah, so maybe I'll put this up for a short bit of a debate. So if the model is trained and then we want to fine tune it, you know, is it possible just to like directly start training that model on the reward for the new task? Does it seem like that would make sense? Maybe. Has anyone tried something like that before? Just for fun? No, not so much for fun. You did it sort of like for pain instead. Uh, okay. It ends up being really difficult. The Because we've got this like paradigm, like for normal all like an LLM that would be fine tuned. It's always just like improve. There's going to be some reward function, and then the loss is going to be plus like some KL term for what's the current policy and the difference between, I'll call this one, yeah, policy B, something like that. So normally something like this has to be performed where like this is basically a constraint on the right. You can do RLHF on some big foundational model. You've got some at least new reward function on the left you want to optimize, but there's this really important constraint for like, don't get too far away from the model that was trained already. If you do that, the model either forgets all of that knowledge. So it's kind of like, great, from this, you've made a specialist that is like maybe not totally useless, but very specific to that task. And now there ends up being, some kind of maybe I'll put a lambda in there, this sort of weight between like, all right, how much does the algorithm going to allow itself to basically change this model in order to be able to do well on this new task? And there's this really delicate game going on here with whatever foundational model we make. Okay. But then, so the problem is for offline RL, this doesn't work at all. Okay. So we can't just constrain to this sort of like just specific model. Like here's the policy, don't get too far away from that, partly because of compounding errors. And the thing that's worked so far is actually basically not this, but it's more like DKL and then like from the actual data set. So the problem is now is if we want to do, even in the fine tuning process, we need to keep around all the data that was from offline RL. So actually this causes some kind of weird challenges. So now if we have to keep around all that data, could consume a huge amount of like actual space on the computer and you're already generating stuff. But it also causes these other two slightly more delicate problems. So this is one example of this. So this is basically the blue line is without retention. So it's like trying to train from doing like offline RL and then just basically at some point, no more of the old offline RL data, only online data. Technically should still be able to keep training. Technically, yes. But here it actually performs quite poorly. So at least for like IQL and CQL that we've discussed a few slides ago, in this transition process, basically it looks like the Q value is completely wiped out. As soon as it goes to, surprise, surprise, there's now this data distribution change again to this new task. And if it doesn't keep around all this old data, this is a larger looking change in the distribution, right? Because here now it's like there's no more old data. It's now receiving, it's been like teleported somewhere else and has to perform really well there and continue learning just how it was. And as we know, it's like this is not going to be a very gentle nudge to that fall of statistics that is like the deep policy that we need to only carefully make small movements in order to get it to perform well. So then this paper is basically trying to figure out, okay, how can this process be done such that, fine tuning works better? It doesn't need to have all of that offline data around either. So it's trying to achieve like both of these goals. Okay, does that make sense so far? All right, cool. So then basically what ends up happening is there's this version here. So kind of similar to some of the works that we're looking at for being able to scale like Q learning from on Wednesday. If there's now three versions, there's basically this. The mixed is basically for these different algorithms when it's always a mix between the offline data and the new data. So in this case, it's kind of like just at some point, a little bit more data is now being introduced to the distribution of data. So there's not a big change here. So typically this blue line tends to work a little bit better because it doesn't always get such a significant change. And then you can see that like when it's a complete change to a new data set, like this orange line, especially for CQL, is just basically like starting from scratch. It almost gets no benefit from any of the pre-training from beforehand on an offline data set. To be honest, I'm even a little bit surprised it's able to climb back up to this high value, which means it's still got some plasticity. It wasn't totally wiped out in the training process. That was probably like a good hyperparameter choice, maybe a bit of luck. And there's a bit of this like partial mixed version, which kind of works, but it definitely still has some dives and some challenges. So this is kind of starting to indicate that, in one way, it can be more smooth in order to be able to still include the offline data so that there's kind of a smaller transition. So like the statistics, even for our optimization, can still handle this transition. But the problem is this causes a different issue. So one, we really don't want to keep around the offline data, partly because it gives space, but actually because it makes our algorithm worse. Like the final asymptotic performance. I'll put it this way, which might help it work a little bit better. So let's all pretend we had to learn 10 different tasks. You can pick like 10 different kitchen cleaning tasks. And then actually the task I'll ask like all of us about next is now we're going to go, I don't know, go and shovel snow. Seems really like a great idea right now. But now you have to split your time between now these 11 tasks for how to learn all of them. And that's how this is training. So like maybe including all this offline data makes the optimization statistics more smooth. But now like only 9% of your time is going to be training on new data from your most recent task. So it actually kind of pushes down our asymptotic performance of being able to perform well on our new task. Because now we're using like 90% of our time studying stuff that may be unrelated and at least not picking up on what is important about the new task. And this is one of the motivations for this paper as well, like trying to get rid of this dependence on offline data, because it is basically like a big weight keeping asymptotic performance from being able to accelerate. And that's what sort of is shown here. So like once this is achieved, and basically what they did is a little bit of a balance called this warm start reinforcement learning. So basically some initial part we're doing offline RL, and then it will start to reduce basically the amount of data that's included from the offline data set after it does the transition. And then from there, it can, at least for some of these algorithms, perform much better. So all these other algorithms are much more like just offline. So it trains much faster. It's able to at least use some of the pre-training from offline RL, and it doesn't have quite as many issues here. So it's also getting better asymptotic performance on the actual tasks. Okay. So questions? Is this a great compliment where like actually you're saying, Glenn, you explain things too well. Everything is perfectly clear. I've got my doubts because like even going over some of these papers that I read myself, they're not completely clear because there's always details missing. So I'm sure if someone went to go and implement one of these, you'd probably have like 100 questions. But maybe keep that in mind. But yeah, any other thoughts? Okay. Because this is basically, so now we're kind of getting back into like fine-tune land. And this doesn't, it's not as popular, or at least it's not as easy to do this for RL, like direct RL. We've talked about behavior cloning where we can at least pre-train a policy, and now we can pre-train a queue function. And we'll start to talk about on Wednesday, we'll just have actually a discussion in class, like, okay, which one of these pre-training methods is going to lead to better fine-tuning and why? And there's a lot of weird details. Some of them are engineering details about one of them is now going to require more models, so it'll probably be harder to debug all this stuff and get it to work. But the other one might learn a better representation that's better for fine-tuning later on. Okay, any other questions? Everyone's just excited to take off for the weekend and go skiing? All right, good. Yeah, that's it for today. So that's going to cover everything for offline RL. Otherwise, enjoy the weekend. Try not to get trapped by snow. Have a good time. And ask questions if you've got any about the projects online. Otherwise, I'll see everybody on Wednesday.